All right, we march on through Thomas's Chapter 8 in Math222 at SUNY Geneseo, today with a look at not how to find an integral per se, but at how to approximate the value of an integral. If I have a definite integral and I don't know how to do it, and an approximate answer is good enough, what tools are at my disposal to do that? And some of those you're already very well familiar with. Oh, let's go calligraphy pen. You're already well familiar with. So we imagine you have some function f of x on some interval from A to B. And you remember from Calc 1 where you would say, well, let's split this up into a bunch of subintervals where this is x sub 0 and x1, x2, x3, x4. And we would make rectangles on those subintervals. You remember from Calc 1 a whole lot of rectangle making. And if we used the left endpoints of each interval, then we would say that a left rectangle approximation method would mean that the integral from a to b of f of x dx was approximately equal to the areas of each of these rectangles. So we would have the height here is f of x naught times the width, x1 minus x naught, and then the height here, f of x1 times the width here, x2 minus x1, and then the height here, f of x2 times x3 minus x2, and then the height here, f of x3 times x4 minus x3. And so you'd add up the four blue rectangles, and that would be approximately the area under the curve. And then somebody said, well, the left endpoint, well, who gets to do the left? Why don't we do the right? Why don't we say that the area under the curve is approximately equal to, okay, we'll take the right endpoint and use the right endpoints to determine the heights of our rectangles, and that seemed like a fine idea at the time. And so that's f of x1 times that change in x, and then f of x2 times that change in x, and then f of x3 times that change in x, and then f of x4 times that change in x. And everybody remembers those. And some teachers probably talked about a midpoint rectangle approximation method where we would do a midpoint of each interval and say that the area from A to B is approximately, well, take that midpoint and let the midpoint determine the height of the rectangle. Take that midpoint and let that determine the height of the rectangle. Take that midpoint and let that determine the height of the rectangle. Take that midpoint and let that determine the height of the rectangle. So in each case, you would have the sum as n goes from 0 to 3 of f of, let's see, so it's a function value at x sub n plus x sub n plus 1 over 2, that's just the height at the midpoint, times the change in x, which would be like that, and that's only because I don't want to write them all out, but again, this is just add up all the green rectangles. And this is all stuff that you're familiar with. I assume because you passed Calc 1 that you can do a left rectangle approximation method and a right rectangle approximation method and a midpoint rectangle approximation method. There are other methods. For example, there's the trapezoidal approximation. When we do the trapezoidal approximation method, we imagine some function, f of x, from some interval from a to b, and we imagine breaking up the interval into a variety of subintervals So this is x naught, and then x1, and then x2, and there's a bunch of them, and then b is x sub n. But instead of using rectangles, we're going to use trapezoids. And we use trapezoids in the following way. Let's go purple. We use trapezoids in the following way. We connect this point to that one with a straight line, 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 and to that one with a straight line, because when we drop these segments down, the shapes that result are all trapezoids. Now, the tremendous advantage of using a trapezoid is that the area of a trapezoid is half the height times the sum of the bases. And these are all trapezoids that are, so to speak, on their side, where the heights are all these little jobbies. So if we keep all of the intervals of equal width, then this trapezoid has an area of whatever the change in x is over 2 times this height plus that height. Well, this height is a function value at x naught, and this height is a function value at x1. And then the second trapezoid has a height that's whatever this delta x is, and then these bases are f of x1 and f of x2. And we could keep going until the last one, the height is delta x, and then you have f of xn minus 1 and f of x sub n. And then you think to yourself, every one of these is going to have a delta x over 2 if we keep the delta x's all the same. If we don't keep the delta x's all the same, then we have to figure out each of these individually. But if the delta x's are all the same, then we say that the trapezoidal approximation with n subintervals is delta x over 2 times, and then what do you got? You got an f of x0, you've got an f of x1 and another f of x1, that's two f of x1s, and then you got an f of x2 and another f of x2, so all the ones in the middle, there's two of them, right up to this last one, and then the one at the end is just by itself, f of xn. So how does that look practically? Well, practically, let's pretend that we have f of x is x squared, and we're looking at the interval from 0 to 2, and I want to approximate the integral from 0 to 2 of x squared dx with a trapezoidal approximation for subintervals. For subintervals. So we know what those little boundary points are going to be. And so we think that the trapezoidal approximation with 4 subintervals is delta x over 2 times the first y value, 2 of everybody else, and then the last guy. So what's that? Well, the delta x's are all a half, and then the y values are determined by looking at the function. 0 squared, half squared, 1 squared, 3 halves squared, 2 squared. 0 squared, 1 half squared, 1 squared, 3 halves squared, 2 squared. And this turns out to be 11 fourths. Turns out to be 11 fourths. Or, if you like, we could take a look at sine x on 0 to pi and try to come up with that, with an approximation for this integral using 4 subintervals. So if we try to do a trapezoidal approximation with 4 subintervals, we really know where those lie, and that's just arithmetic. And so we'd have a delta x over 2 times the first y value, 2 of all the others, and then the last y value. So what's delta x? Well, delta x is pi over 4 in every case. And then your y values. I know what this one is, and I know what that one is, and I'm pretty sure I know what this one is. Do you remember what the sign of pi over 4 is? Good. And this thing turns out to be pi over 8 times 2 plus 2 square root of 2, and that is an acceptable form of the approximation. Okay? We should talk about the error bound on the trapezoidal approximation. How good is the trapezoidal approximation? How good is the Trap app? Well, I'll tell you, if you let capital M be an upper bound for the absolute value of f double prime on the closed interval AB, then the error on the trapezoidal approximation is less than or equal to whatever that value of M is times the length of your interval cubed over 12 times the square of the number of intervals you used. So let's see, in practice, I'll go back a couple of slides here. In practice, f prime is 2x, f double prime is 2. What's the greatest that f double prime can be on the interval from 0 to 2? That's it. Capital M is 2. So the error on this approximation, the biggest possible difference between this and the actual retail price, is less than or equal to capital M times b minus a cubed over 12 times the number of intervals squared. And this turns out to be 1/12. So what does that mean? That means that this number is within 1/12, high or low, of the actual area under the curve. And we could do the same thing here. We could figure out what f double prime is, what the maximum value of f double prime in absolute value is from 0 to pi. I'm guessing it's 1. And then we could crank out how far this is from the actual retail price. The upside here is that we know the wider your interval is, the bigger this numerator is, and so the bigger your error can be. But the more subintervals you use, the better your approximation is, because the more intervals you use, the more subintervals you use, the bigger your denominator is, the lower your error is. Okay? Okay, so I would like to talk about one other thing before we're done. I'd like to talk about Simpsons Rule. Simpson, eh? Yes, Simpson. Simpsons Rule comes from parabolic splines. Instead of using little trapezoids, we take 3 consecutive x values and fit a parabola to those 3 points. And then we take 3 more and fit a parabola to those 3 points, and so on down the line. And when we do that, Simpsons approximation with n subintervals is delta x over 3. We require that the delta x's are the same, delta x over 3 times the first y value plus 4 times the next one plus 2 times the one after that plus 4 times the next one plus 2 times the one after that, and so on, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, until the next to last one, there's 4 of those, and then the last guy hanging out by himself, like I did for my whole childhood. Simpsons approximation. You don't have to know how to fit parabolas there. Simpson figured out how to fit parabolas there. You've just got to know 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 1. So just by way of example, let's take this. This is sine x on 0 to pi. Takes longer to draw than it does to actually figure out. So if I were to use Simpsons rule with 4 subintervals, I'd do delta x over 3 times the first y value, 4 times the next, 2 times the one after that, 4 times the next, and then I would continue 2, 4, 2, 4, 2, 4 if there were other subintervals, but there aren't, and then the last guy. And this turns out to be pi over 12 times 4 radical 2 plus 2. So why do we like Simpsons rule better? Well, the error bound on Simpson's formula, how good is Simpson? Well, Simpson is this good. If m is an upper bound for the absolute value of the fourth derivative of f on AB, then the error on Simpson's rule is less than or equal to that value of m times b minus a to the 5th power over 180 n to the 4th. Now, I don't have to tell you that 180 is much bigger than 12, and n to the 4th is much bigger than n squared. So this thing gets small really, really fast. In fact, in this case, the error on Simpson's approximation is less than or equal to, well, you can imagine the fourth derivative on this is that, and the biggest it gets on 0 to pi is 1 times pi minus 0 to the 5th power over 180 n to the 4th, and this is approximately 0.00664, and that's a pretty good approximation with 4 subintervals. So imagine if there were 8 or 12 or 16, you could get really, really close really, really fast. All right, so I'm just about out of time, so I've got to give you a quick OYO, and here's the quick OYO that I'm going to give. This is y equals 1 over x. On the subinterval, on the interval from 1 to 2, figure not drawn to scale, I would like you to approximate the integral from 1 to 2 of 1 over x dx using a trapezoidal approximation with 4 subintervals and Simpsons rule with 4 subintervals. Get some approximate answers. They should almost match, and they should both be almost what the actual retail price is, and you can figure out what that is. Okay, so that's our talk. Glad we had it. And next time up, we take integrals to infinity.